Everyone, I am Qing Xu, a research assistant professor from Tsinghua University. In today's Future Automobiles class, we will talk about intelligent and connected vehicles in China. As the host, the organizer suggests to us, if you have any questions, please feel free to write them in the Q&A section. There should be a Q&A section in the Zoom Zoom system. A research assistant professor from. Okay, I'll adjust the camera here. Is that okay? Please feel free to ask questions in the Q&A sections. By the end of the class, I will try to answer one or two your questions, and I'll send back the answers to the other questions later. All right. So today's class, we will discuss about the ICVs in China. First of all, I would like to quickly discuss the background and localized ICV solutions in China. Intelligent and connected vehicles, which is also called connected and automated vehicles in the US, is the fusion of autonomous vehicles and connected vehicles, of course. It brings out new products, new paradigm, and new ecosystems. As shown in this picture, there are two approaches to develop intelligent and connected vehicles. One is to develop onboard intelligence, like to equip better computers or onboard embedded system and better sensors to develop toward autonomous vehicles. The other one is to develop connected intelligence using the V2X and roadside cameras and sometimes maybe the cloud toward the connected intelligence. Different from the conventional vehicles, there are two major features of intelligent and connected vehicles. Number one is the interdisciplinary and cross-industry integration. So as shown in the slide, unlike the conventional vehicle, which is a mechatronic product, ICV requires the fusion of the mechatronics and ICT technologies, including the communication, computing, and so on. This underlines the industrial integration of automotive, transportation, information, and communication technologies. And number two, ICV has strong regional and social properties. The operation of ICV requires support of telecommunication, maps and data, and so on, of which under security monitoring, due to the national security sensitivities. So each country, including China, has its own standard and regulations. Localized factors exist in the development and application of ICVs. The Chinese government promotes the policies and regulations for the ICVs very actively. The government has established some cross-department coordination process and formed some top design for the development of ICVs. For example, the Ministry of Industry and Information Technologies launched the ICV Development Action Plan, which is very important. The Development and Reform Commission launched the ICV Innovative Development Strategies. The Ministry of Transportation strengthened the product application and the pilot demonstration, and the Ministry of Natural Resources expand the market of map and the positioning applications. For example, the Innovative Development Strategy of Intelligent Vehicles released by the NDRC, which is short for National Development and Reform Commission. In their strategy, there are both long-term vision from 2035 to 2050 and some short-term goals up to 2025. For the development of ICVs, they try to stimulate the enterprise establishment, market fostering, and some infrastructure development and deployment. A localized solution for the ICVs in China is very necessary. There is yet no experience of successful applications of ICVs exist any where any country in the world. The localized solution of ICV innovation and development in China shall be planned not only according to the need of technology and industry development, but also there are some specific conditions in China that should be considered. So to develop automated driving vehicles, there are two approaches. Number one, shown as in the first picture, the incremental paradigm of vehicle intelligent level improvement. This means to gradually increase the intelligence level for the automated vehicles from level 1 to level 2, level 2 to level 3, level 3 to level 4, and so on. However, current gaps in the automotive electronics, control, and actuator designs in China would be continuously expanded following this process, and might result in, here shown in the slides, hollowness of the core technologies in the automotive industry. Another path is to focus on some high-level autonomous vehicles. If China do so, China might end up in an embarrassing situation due to some critical disadvantages on some core technologies. Currently, China is developing the sensor MCU and some toolchains, but that's not enough. So thus, China is trying to focus on some localized properties of the intelligent and connected vehicles. The communication, map, and data would be important for the localized solution for the SUVs in China. What is the localized SUV solutions? The localized SUV solutions in China should follow the following three standards. Number one is to comply with Chinese infrastructure standards, including the standards for the roadside infrastructure, map data, V2X communication, and so on. Number two, they should follow the Chinese connected operation standards, including standards of the SUV access, supervision of connected operation, information security, and so on. Number three, they should comply with the new standard architecture of automotive product in China, including standard of intelligent terminal, intelligent onboard computing system, the cloud control platform, and so on. That requires us to develop and design and develop some unified fundamental technologies to support the automated driving applications. So to do so, the experts in China had a long-term discussion, and 5 basic platforms. The conclusion was that 5 basic platforms must get developed, and they are the basic computing platform, basic intelligent terminal platform, basic cloud control platform, basic dynamic HD map, high definition map platform, and cybersecurity platform. Those 5 basic platforms will provide fundamental and common technologies for the automated driving application developers and decouple them from the unique Chinese standards. To better understand what we said in the last slide, we can have a discuss in this slide. So currently, there are OEM, Tier 1 and Tier 2, maybe Tier 3 and so on. Tier 1 companies provide the product to the car OEM, and Tier 2 companies provide some key components like chips or core system, or maybe some IP cores to the Tier 1 companies. In the future, there will be some space between Tier 1 and Tier 2. We call them Tier 1.5, Tier 1.5 companies. Those companies will work on some new crossover technologies, like the basic software architecture, some AI applications, and so on. And the basic platform components and services shown in last slide will be the output, will be their product. So in this slide, we take the basic onboard computing platform as example. The companies below the tier 1.5, they provide the basic computing platform, which include the chips, IP cores from the tier 2 as before, and the tier 1.5 to provide the ICV OS, which is extended OS concept, some function software, and some basic board reference design. And then tier 1 will use the output from the tier 1.5 and to write and design their own applications and customize their own circuit board, write their application softwares, and provide the product to the OEM. There are some this kind of companies in China already. The CSCV, which is short for China ICV, is a typical company that integrates the resources from the industry and to form a new tier 1.5 basic computing platform company. The automated driving OS, or we can call that the ICV OS, is their main product. All right. This is another diagram describing the relationship among the OEM, tier 1, tier 1.5, and tier 2 companies. Similar to the previous slide, the tier 1 companies get resources from lots of different wide tier 2 industrial chains and try to provide some basic fundamental computing platform with a hardware reference design and ICV OS. The tier 1 and OEM, based on what tier 1.5 provides them, customize their own upper level applications according to the requirement from the customers and provide the product to them. All right, that's the background and the localized ICV solutions in China. And in the following section, we will continue talk about typical new infrastructure in China, the cloud control system. So cloud control system, or we will start by the basic cloud control system. A basic cloud control platform is one of the 5 fundamental or 5 basic platforms in China, as we introduced before. If we get a glance, if we get a glance of the traffic system in the future, with the support of the cloud control system, the vehicles are expected to satisfy safety, fuel economy, convenience, and efficiency. China was one of the first countries to classify the levels of intelligence and connections of intelligent and connected vehicles. In 2016, the levels of the connectivity of ICVs was first proposed in the technical roadmap of the ICVs in China. 3 levels of connectivity were classified, including connected assistance information interaction, connected cooperative perception, connected cooperative decision-making and control. This was an innovative concept and a new path for the industry to develop the intelligent and connected vehicles. Some detailed technical framework were under revision. That means to develop some specific AD tasks, we have 2 approaches, similar as the very first slide at the very beginning. We can either to develop some onboard intelligence, or we can develop some connected intelligence. So an automated driving task can either be accomplished by increasing the intelligence level or connectivity level. Well, the ultimate goal, of course, is still to develop both levels, for safe, efficient, comfortness, and fuel economy driving. To develop the connectivity intelligence, the cloud control platform plays a very important role. Cloud control system, we define that as a new type of infrastructure is required in this procedure. The system, cloud control system, is shown in this slide. It is consisted of vehicles, which include both intelligent and connected vehicles, and maybe some traditional conventional human-driven vehicles. And roadside infrastructures, including V2X communication equipment, some roadside computing device, and roadside sensors, for example, the cameras, radars, lidars, and so on. Above them, there are 3 levels of cloud. The edge cloud acquires data from several road sensor units and handles from the roadside units and also the vehicles directly sometimes, and handles real-time cooperative driving applications. Regional cloud handles city-level applications, and the central cloud handles applications that require some big data analysis. The central cloud is also connected to some national service platforms, for example, insurance, my provider, and so on. The cloud control platform embraces the concept of the cyber physical system, which is also very famous, short for the CPS. So it divides the space to the physical space, the real traffic space we can see and take part in, and the cyberspace, which runs in the cloud. The status of the vehicles and other traffic participators, like the bicycles, pedestrians, and even some, for example, obstacles and traffic lights, traffic signs, everything from the physical world will either get connected or get detected by the roadside sensors, and their data will get collected and sent to the cyberspace through some standardized interconnection interface and communication systems. The digital twin system shown in the gray color here is generated in the cyberspace. Every vehicle, each traffic participators have their unique object in the cyberspace. Overall application and communication task arrangement are handled in the cloud, and the decision and control commands are sent back to the vehicles in the cyberspace. But before sending back to the vehicles in the physical space, they should firstly get calculated in the cyberspace. Sometimes some simulation and the forecast will be done in the cyberspace to verify the decision making and the control command before sending them to the real vehicles in the physical space. This page is a workflow of the cloud control system. Here are the vehicles, pedestrians in the physical space. Here are some roadside base stations. On the base station or on the infrastructure, there are some communication device, cameras, radars, and so on. And this is the edge cloud. This is the region cloud. And there are maybe more clouds above them. So the working flow of the cloud control system is as follows. So first is acquiring those data. Those with communication devices, like the vehicles, can upload their perception and their CAN bus data through the V2X communication, some to the roadside road send unit, some directly to the carrier and then to the edge cloud. The roadside sensors will capture some real-time information from those cannot directly communicate with them. For example, the pedestrians will be detected by the roadside sensors and send their generate their locations and velocities, directions, and so on. And the second step is the data fusion. There are multiple different levels of the data fusion. The roadside sensor will handle the data fusion of multiple different types of sensors. For example, data fusion between the camera and the LiDARs. And then multiple roadside sensors or roadside unit will send their first data to the edge cloud. The edge cloud will perform some higher level multi-roadside unit perception and combine them to one big dynamical map. And higher level, like the traffic flow information, will be handled by the regional cloud perception fusion. And then the edge cloud, regional cloud, edge cloud, and roadside roadside unit will try to compute or to process their calculation tasks. So the roadside unit will handle the calculation task with the highest priority, or we say that requires the lowest time delay, then the edge cloud, and then the regional cloud. By the way, the edge cloud is probably the most powerful unit in this procedure. So lots of the time-consuming tasks like the decision and control calculations should be done here. And some reaction-based calculations will be done here on the roadside sensors. And then they will send the control or decision in result back to the vehicles and maybe warn the other participators like the pedestrians in some ways. For example, some information might be sent to their phones or some roadside screens. And the vehicles and the pedestrians may respond what they get, sometimes the decision data, sometimes the control commands. This is the working flow of the cloud control system. So similar to the example of the onboard computing platform, the cloud control system is consisted of the basic platform, a basic cloud control platform, and cloud control applications. The basic cloud control platform provides some standardized interface functions and some useful tools to the developers. And the developers use the tools to develop their own cloud control applications, like the warning application, the decision and the control applications. The basic platform and the applications form the cloud control platform. If we look at a traffic system in the future, the cloud control basic platform contains the hardware, including some data center. This is the cloud, cellular station here, in charge of the communication, roadside system, intelligent roadside system has the sensors and some roadside computing devices and so on. And they can provide some digital twin information. And the digital twin is a map of what's happening in the physical space to a cyberspace. And some prototypes of some basic fundamental functions that cover multiple traffic scenarios should also be provided by the basic platform, like the here formation control, automated parking, and signalized coordination for the vehicles, and so on. And what the application developer do is they design the applications and form some specific services, like here the shared vehicles, the mobility taxi service, intelligent public bus service, intelligent logistics, and so on. They design their own applications and publish them on the base cloud control platforms, and together forms the whole cloud control system. All right. So we, our lab, did some practice of the cloud control system in Beijing, Shanghai, Changsha, and some other cities in China. This work supported by the Chinese government, and most of the engineering work we have to see in the following slides are done by the startup company of our lab. It is called the Qing Cloud. A roadside system include the, as we talked before, the cameras, the radars, computing unit, some roadside computing unit, some CV2X devices, and so on. The cloud includes the edge cloud, regional cloud, central cloud, and so on. They are connected via either the fiber cables here in the solid line, or some wireless communications here showing the dot line. In this picture, here is a deployed roadside system. This is the radar, looks like this. This is the camera, and for the camera to be able to see the vehicles and the pedestrians, we have the flashlight here. Computing unit is included, is installed here, and the communication devices is installed here. We also developed several mobile roadside units for some rapid testing and validation, verification of our maybe perception or maybe decision algorithms. To actually practically deploy the roadside infrastructures, some algorithms are also developed. This slide demonstrates the sensor model here, and some algorithms here we design that can automatically generate the sensor deployment suggestions. However, practically, when trying to install those sensors, the deployment locations are somehow limited because multiple factors have to also get considered when choosing the roadside sensor deployment locations. For example, if it's in on-ramp or off-ramp, maybe we cannot deploy our roadside sensors there. We need to push forward or go back like 100 meters and so on. So some adjustment and redesigns of course still very necessary. There are some photos of the cloud servers in the data centers that we are currently using. The cloud, that's what the cloud look like, just some servers. And we have some, we use some technologies to ensure they can work 24 hours, 7 days. And we are still trying to improve the software running on the cloud. We have lots of vehicles equipped with sensors, onboard computers, and or embedded system. and some V2X communication devices to verify the functions and test the performance of the cloud control system. Those are the vehicles developed by the Tsinghua University. We also have some other companies also contributed their vehicles and test their performance under our cloud control environment. There is a video. You should be able to see the video if the network bandwidth is good enough. This is an example of the digital twin system. Here is the camera view of the roadside camera, and the camera gets the position and calculates the velocity of the vehicles. And also we have the roadside radars, and so the velocity is not only get by the camera, but also fused by the output of the radars. And also not only vehicles, but other traffic participators like the pedestrian bicycles are detected. Both the object and their parameters are mapped into the cyberspace. As you can see, this blue one is a virtual testing vehicle, and those white ones or gray ones are the digital twins of the vehicles in the real world, in the physical space. So equipped with the digital twin system or the CPS system, we designed some basic functions, including the large-scale perception, coordinated decision-making, and the multi-agent control, and tried to perform some demonstrations and tests. People also used our basic platform to develop their own applications. This slide shows an example, including some accident warning, long-range warning, and highway management, and so on, for the driving assistance, and sometimes give suggestions to the drivers. We're not satisfied in only giving suggestions to the drivers, so we developed some decision and control algorithms, and tested them with automated driving vehicles. As you can see in this slide, there are some of them. Most of them, I have to say, are still under developing and testing, and some of them are having we are demonstrating them in the Yizhuang in Beijing. Some specific systems are developed and applied in practice already. This slide shows some fuel economy driving for the commercial vehicles like trucks and so on, with cloud-based optimization and dynamical map information. So with the help of the processing power in the edge cloud, some complex dynamical programming model and algorithm can be applied and calculated in real time, which is impossible if we only have some onboard devices, especially some embedded devices nowadays. The fuel consumption reduction achieved about 4.0% in typical heavy scenarios. So basically, we use the slope information from the digital map. If we can get some dynamical information from the digital map in the future, like the traffic light information, the intersection information, on-ramp, off-ramp information for the highway scenario, we believe we can achieve much better results in the future. Another application we already have is to use the cloud control system to help optimizing the traffic efficiency. For example, getting the vehicle information from the taxis from the Didi company, the traffic signal can get optimized according to the dynamical requirements. requirements from the taxis and from the other vehicles. The average speed in our test district can increase from about 15 kilometers per hour to about 23, 24 kilometers per hour, which is very significant. So as we already know what the cloud system is, the cloud control system is, in the following slides, we'll discuss specific applications. This application is, we believe, what will happen in the future with the help of cloud control system, which is the cloud-based formation control of intelligent and connected vehicles. A common way to design the ADAS and automated driving is to develop some applications based on different driving scenarios, including like the vehicle following, lane drop bottleneck, ramp merging, intersections, and so on. However, the control logic would be very complex, and it would be difficult to smoothly switch among multiple scenarios, which could damage both driving safety and traffic efficiency. So, a unified decision-making and control framework that covers most of the typical traffic scenarios is required. As we discussed before, the cloud control system excels at real-time data and information sharing, and can provide some high-definition perception results and data mapping results, and so on. The cloud control system is very good at management of multiple applications and can handle large-scale vehicles coordinations. Previously, we discussed about the two roads for the development of intelligent and connected vehicles. And the connected intelligence is a road of developing ICVs, the key road of developing ICVs, at least in China. And currently, there are some existing researchers on this field. For example, some researchers focused on the single-lane platoon scenario, which is obviously too simple to get practically applied. Some works on the multiple platoons, which means only the leading vehicle or the preceding vehicles have the intelligence, and the other vehicles just follow them. And there is only the coordination among the preceding vehicles, which is not enough. And some research work on the lane assignment only lane level assignment, no detailed vehicle control. They just tell vehicle A, you go to the lane 1, vehicle B, you go to the lane 2. They don't care how the vehicle achieves their goals. And what is most interesting is a multi-lane formation algorithm. But what we found, most of them lacks of switching among multiple scenarios. They only focus on some specific scenarios. To take a look, this page shows some popular method for the multi-lane formation control. Number one is the slot-based guidance. There are some virtual boxes on the road generated by the cloud, probably, and the vehicles choose the boxes they want to follow and control themselves to follow them. However, the vehicles and infrastructures operate separately and the lacks of optimization. Number two, a bunch of researchers focus on the steady state formation control and the lacks of the consideration of the scenario switching. Number three, some researchers work on the formation structure change. They try to find a method to dynamically change the formations, but some of them use some centralized optimization method like the large-scale nonlinear MPC, which could be not applicable in real world because a lot of calculations are required, so cannot achieve real-time calculation. And most of the researchers require predefined vehicle orders. Thus, they are not flexible enough for real applications. In our research, there are two tracks. Thrust 1 focused on the road segment scenario, including multi-lane and run ramp and off ramp and so on, and develop some multi-lane formation control method. Those multi-lane formation control will be shared with Thrust 2, which applies the formation control method to the intersection scenarios. So Thrust 1 provides a formation control strategy, and Thrust 2 provides a formation structure requirement and send back to what we get in the Thrust 1. Formation control of multiple vehicles solves the problem of steady driving of a group of vehicles, structure reconfiguration when the driving scenario is changed, and vehicle drawing and leaving management. The structure of formation can get switched according to the change of driving scenarios. For example, the scenarios could make the formation control. The formation we are having formation control here, but the lane clearing scenario, which means there are some other conventional vehicles, and the lane drops. So we have to change the formation from 5-lane formation to 4-lane formation. Similarly for the lane drop scenario. Here we introduce a multi-stage framework of the cloud control formation control method. The initial position of the vehicles distributes randomly on the road, and we expect them to drive with some specific structures, which is predefined by us, but the order, pay attention to the order. The orders are not predefined, but only the structure is predefined. So there are two stages for the vehicle's motion. One is the structure switching stage. The other one is the steady driving stage. We propose a centralized planning method to organize the behavior of the vehicles, which of course, as is centralized, should be running on the cloud. The vehicles are close to their desired positions and the threshold is satisfied. They change from the switching stage to the steady stage. And then when the scenario change is detected, they change back to the structure switching stage. We use the centralized planning to calculate the conflict-free behavior of the vehicles. And for each vehicle, we use a decentralized control to calculate the control input for the vehicles. Given that it is hard to control the vehicles from the real world perspective, because vehicles drive with different speed and have complex conflicts. So we measure the desired speed of the formation from the speed of all the vehicles, and we can then get the relative speed of the vehicles, which could be easier for us to use. And then the relative coordinate system is built. The coordinate contains the relative several relative integer points. They are discrete. That the discrete integers laterally they are distributed by length and longitudinally distributed by the Fallin gap, predefined Fallin gap. And by defining the available position of the vehicles in the native, in their relative coordinate system, we can then get two standard geometric structure by intuitively. The interlaced one, the picture in the left, and the parallel one. Since we try to aim to improve the safety and the lane change efficiency, here we choose to use the interlaced structure as a standard formation structure. In the relative coordinate system, vehicles occupy some points to form interlaced structure and can temporarily stay on their points when they are changing the structure. So a pair of number is used to represent the coordinate of the vehicles, the len ID, which is x, and the y, which is a layer ID. Besides, we define the achievement points for the vehicle at each timestamp. Relative motion mode 1 represents the vehicle could drive to their other 8 points, their neighborhood points, and also including their current point in one timestamp. And relative motion mode 2 represents that they can drive to the surrounded 4 points and the current point in each step in order to regulate the motion of the vehicles and avoid collision. We assume that the duration of each movement takes the same time. So before the motion planning, we need assign vehicles to their target locations. Different assignment may lead to some unsolvable conflicts among those vehicles, which lead to some car accidents. Target assignment is a classical problem in robotics motion planning and control because the robots usually have very, they can perform straight strategies, and the speed of the robots are usually relatively low. However, in the vehicle target assignment, we need to consider some complex constraints and avoid a collision between or among the vehicles. In order to assign the vehicle target, we should define the cost of the assignment at first by applying the A-star algorithm for the vehicles to calculate the cost of the vehicles need to travel to their target locations, which is then defined as the cost. Then the cost matrix, short for C here, and the assignment matrix can be defined accordingly. And some target assignment problem can be modeled as an integer programming problem. There are many mathematical algorithms already, and they are designed to solve this kind of assignment problem. And the Hungarian algorithm is one of the most commonly widely used one, which can calculate the optimal assignment with a minimal cost. As mentioned before, because of the complex constraints of the vehicles, some of the assignment may lead to some inevitable collision. So here we define 3 types of conflicts that may cause the collision because the trajectory of the vehicles will overlap. So here vehicle 3 and vehicle 4 is the first type of conflicts. If vehicle 3 stops here, it will block the way of the vehicle 4. So the vehicle 4 is conflict with vehicle 3. And there are 2 other types of conflicts shown in this slide accordingly. And we can prove that only the first type will cause the collision. Besides, we found that the first type of conflict can be resolved by exchanging the target of the 2 vehicles. And this exchange will not cause new conflict, we can prove as well. And all the conflicts will be resolved in finite steps. Based on the defined algorithm and assumptions, we can then build some coordinate map to describe the motion of the adjustment of vehicles. In this slide, there shows an example of 2-step process for the formation structures reaching step 1 and step 2. And the coordinate map is built to detect the collision. Once a collision is detected, the conflict solving algorithm will be used to solve them. This is the same example as in the last slide, where the vehicles change from the 5-lane formation to 3-lane formation. And the upper part shows the movement in the relative coordinate system. The lower part shows the state in the real world. The points in the real world are the key points, as we discussed before, and they are used for the vehicle trajectory planning. The vehicle need to plan the trajectory on their own to follow their the key points. So algorithms before this slide are done by the cloud control system, by the cloud, by the server. And here, the slide after this slide are done by the vehicles. Since a vehicle should pass a sequence of points to achieve its target, the multi-stage trajectory is planned based on the Bezier curves to perform single lane change and dual lane change and multi-lane change and so on. The right point represents the key road points corresponding to the points in the relative coordination system. And the time for the vehicles to travel on each segment is the same. We have to make them the same. So as for the longitudinal control, we can calculate the length of the trajectory as their input. Our goal is to control the vehicle to arrive at each point at the desired time, strictly at the desired time. The state of the vehicle is fixed as the initial and terminal or the final points, and they have the spatial temporal constraints as the intermediate points, the points in the middle right points, they have to follow the spatial temporal constraints. The second order state equation is used to model the longitudinal behavior of the vehicles. And then the control energy, we use accelerate is calculated as an objective function. Thus, the longitudinal control problem is modeled as the optimal control problem, and with the state equations, interior points of the constraints, initial and terminal constraints, and the boundary constraints, we can solve this equation. As for the control inaccuracy, since we use the PID preview control as a lateral control method, the inaccuracy may accumulate over time. And we model our longitudinal control problem into a multi-stage long-term control problem, which may also lead to some accumulation of inaccuracy. Thus, we use the rolling horizon framework to replan the control input after some fixed steps. We will not talk too much about them today. Okay, in this slide, we provide an example of how to use to show the relative motion, relative state, and what happens in the real world. The green vehicle needs to catch up with the other 4 vehicles already to form a 5-vehicle formation. And the first step is to move forward by one layer and change to the right lane. And the real world motion 1 shows its trajectory. And for the second step, it should accelerate. The vehicle must move forward 1 more layer and successfully join this formation. This is what happens. So we summarize the method of the multi-vehicle formation control into the following 3 parts. Number 1, the real world status. And number 2, centralized planning. And number 3, decentralized control. The centralized planner in the cloud they can detect the real-world changes and chooses the desired formation structure and generates the target locations and actually target states, because that's including location and velocities for the vehicles. And vehicles are assigned to the targets, and some conflict-free motion to travel to the target are also calculated and planned. The decentralized controller on the vehicle plans the trajectory according to the relative path, and some multi-stage control input are calculated for the vehicle control, and the control commands are sent to the actuators. The process changes the state of the group of vehicles to adapt the driving scenario. Okay, so this is how the closed loop works. We did some simulations to verify the function and evaluate the performance of the proposed method. Case study is firstly conducted. The circle represents the key points, and the lines with specific colors represent the target, the trajectory of the vehicles. So this video shows from 3 lanes to the 1 lane formation. In the second case, vehicle change from a three lane formation to a 2 lane formation. And this process takes 2 cycles. And this case, there are 8 vehicles change their formation from 3 lanes to 4 lanes in 1 cycle. We also did some more simulations in a lane drop bottleneck to verify the performance. The length of the scenario is about 1,000 meters with the lane drop bottleneck, and the benchmark method, the compared method, is the default model in Sumo. We also did this simulation in Sumo. There could be some cause of the congestions at some high vehicle volumes if we only use by the default model or the default method in Sumo. As you can see, the figure shows the result of average traveling time of all the vehicles, where the blue lines shows the result of the benchmark method, Sumo method. The red line shows the result of our formation control method. It indicates that the formation control method keeps a low travel time under all the input volumes. The x-axis is the volume. But the travel time on the benchmark method become higher when increasing when the input volume is higher than about 1,000 vehicles per lane hour. It shows that formation control method achieves higher traffic efficiency. This video shows the process of the formation control method under 3 different input volumes. You can see that under these 3 volumes, the formation control method can smoothly control the vehicles and change their lanes to keep a steady and high speed. If we put the method together, we can see that the benchmark method leads to congestion with the formation control method. Well, the formation control method can still keep high efficiency and no congestion happens. That also tells us we really need cloud control system. We need communications. We need coordinates among those vehicles in the future. Even if we can develop very high level onboard intelligence, the vehicles could be selfish, and the lack of the optimization of the whole traffic system, they can still lead to some traffic congestions. The spatial temporal distribution also indicates the same result. We won't talk too much about this slide. We also conducted simulation in the color simulation environment and evaluate the performance of the formation control method in multiple traffic scenarios. The figure in the right-hand side shows the route of the vehicles in the simulation. Yeah, as we tested before, there are some issues playing these videos, so I'll directly drag it. So this video shows some relative state of the vehicles in the left, and in the right shows some real world motions of the vehicles. Of course, the real world means those in color. There are 6 vehicles in the very beginning. Another vehicle joins them, and the lane drops from 4 lanes to 3 lanes. So the vehicles change their lanes coordinately, and then the lanes go back to 4 lanes, and the cloud tell them to change back to 4 lanes. The vehicles calculate and perform the lane change. Okay, and there are some more scenarios as we discussed in the beginning. There are some conventional other vehicles. The vehicles can change their lanes to pass them, and this method also can be used in some lane drop scenarios and other scenarios and so on. All right. Oh, the video is working. No. All right. So if you remember, we try to discuss if we can have a unified method that can cover multiple traffic scenarios. We only discussed about the one-dimensional scenario. And now we will talk about the two-dimensional scenarios. Some typical challenging scenarios like the multi-lane on-ramps and the multi-lane intersections and so on. We would like to extend our previous method, to the two-dimensional scenarios and solve the problem that existing method usually consider only some particular scenarios and lacks the generality. So the idea is very simple, but before that, we will see what existing method already have. There are some existing method that can be applied to both single lane and multi-lane intersections, like the reservation method, which is a classical method, and some virtual platoon method. We will discuss this method a bit. The idea of this method as an intersection is to form virtual platoons and to let all the vehicles coming from different directions to pass the intersection one by one. And the sequences were determined based on the distance of the center, the distance of the vehicles to the center of the intersection. And the method need to define some virtual leading vehicles and provide some following input for the real vehicles. And therefore, the disadvantage of this method is very obvious, that it only considers one-dimensional geometry topology, which result very low traffic efficiency, because usually we have not only a platoon but multi-lanes. So geometric topologies with some high traffic efficiency is required. To achieve that, we first need to build some conflict model of the unsignalized intersections, including crossing, merging, and diverging conflicts, as you can see. Based on the conflict model, we can then number 12 traffic flows coming from 4 directions to calculate whether they are conflicts or not. And based on this, we can draw the conflict relationship in the diagram or in the graph, and we can use graph theory to solve this problem. Give an example, we can draw the vehicle's conflict relationship. This has a vehicle with different IDs coming from different traffic flows, and we can draw the vehicle's conflict relationship graph based on the conflict graph. And with the help of the graph theory, the depth-first spanning tree can be deployed to calculate the conflict-free geometry topology. So before proposing our method as a multi-lane unsignalized intersection, we have two questions. That is number one, is a virtual platoon method extendable in a multi-lane intersection? And number two, will organizing vehicles in the formation really improve the efficiency in a multi-lane intersection? So first of all, we check the conflict relationship to ensure the safety. Similarly, depth-first spanning tree is also used to determine the conflict-free passing sequence. But the difference is that the definition of the conflict constraints could be extended. You can see in the picture, the definitions could be different, and the passing sequence with the same coming sequence could be different. Then let's see how we have improved the virtual platoon method. Consider the vehicle coming from northeast, south, and west for directions in unsynchronized intersection. We rotate them to parallel lines and make it easier to watch. And what in the left is a stop line, so the vehicle comes from the right to the left. Then let's look into whether organizing vehicles in the formation could help in improving the traffic efficiency. We still start from the single vehicle platoon, which means a single vehicle is considered as a node in the same as in the classical method. Utilizing the depth-first spanning tree, a possible passing sequence can be obtained, as shown in this slide. So the virtual platoon consisted of single vehicle in each layer. Now we consider another virtual platoon that is consisted of multiple vehicle formations in each layer. In this virtual platoon, it treats subgroup of vehicles instead of only one group as a node in the spanning tree. So we can get the same result, but each node indicates multiple vehicles. Similarly, the same still for layers. So after passing sequence is generated, we found it is possible to compress the platoon by sharing longitudinal space in one layer. So those subgroups without conflicts, for example, the green vehicle in the second layer can furthermore push in, and those with conflicts cannot. So a compressed formation can get generated. The layers is from 4 layers to 3 layers, which means we are saving some time, achieving some more efficiency for the traffic system. All right, so here shows the final process in the multi-lane intersection. At first, some messy vehicles get together to form a multi-lane formation based on the method we talked about before. And then the formation was divided. The vehicles are assigned and form some subgroups here. And then we treat each subgroup as a node, as a single vehicle like before. The depth-first spanning tree method is applied to generate the conflict-free platoon coming from all the 4 directions. As you can see in this slide, I'll just skip to this slide because of the time. I'm not sure if the resolution is good enough for you can see, but this animation shows the vehicles could pass the intersection without the collision. And also, we can summarize them like this. The virtual platoon method is still very efficiency in the multi-lane and synchronized intersections, and compared with the single vehicle control, the multi-vehicle virtual platoon method can further improve the traffic efficiency. And finally, we will give the summary. So in the slides today, we discussed about the background and localized SCV solutions in China. We know that China is promoting 5 fundamental or basic platforms. Take the basic cloud control platform, for example. We discussed the structure, the details, the architectures of the cloud control system, and it is a new type of infrastructure for the traffic systems in the future. And we also discussed the application which can be applied for the cloud control system, which is the formation control for the intelligent and the connected vehicles. All right, so that's all for today. I'll be glad to take some of your questions. Let me see the Q&A sections here. So I got 2 questions. Number 1 is how to prevent systematic safety accidents of ICVs. How should we make decision when simultaneously interpreting the signals from different sensors? For example, the data from the vehicles is inconsistent with the data from the roadside sensors. Okay, this is very important questions. So those guys who are working on the perception is making a lot of effort on the data synchronization. In our research, there are 2 things are considered in our research. Number 1, the data, of course, can either not get synchronized or cannot get real time. We want the real time data because we want to know what is really happening in the environment. So some of the data, we give up some synchronization and try to use the data as some delayed data. Actually, with the communication, not only data delay, but some quantization and truncation will be also included. There are some communication chains between the roadside sensors, the cloud, and the vehicles. So when designing the vehicle controllers, we have to consider them. We should use some predict method to predict the locations of the vehicles together with the onboard sensors, and also should design some vehicle controllers that can adopt those delays, truncations, and quantizations. And number 2 is how to ensure the safety. We all know that the cloud might not be that reliable, right? Or computer or laptop or desktop freezes, it happens. And the communication is not stable enough too. The communication, the 4G or 5G or later, is not that reliable. So the final decision-making and control should be handled by the vehicle itself. There should be a sandbox on the vehicles. There should be a supervisor in this sandbox. The supervisor watches what's happening in the surrounding this vehicle, and also listens to what the cloud sends to the cloud tells the vehicles to do, including some decision making and control these commands. If the supervisor decides, okay, there are something wrong, it is unsafe, so the supervisor should cut off the cloud command input and take over the control of the vehicles. So the safety is ensured by the, we can call it a sandbox mechanism, which is an onboard mechanism. All right, and question number 2. In what ways will the popularization and promotion of smart cars change people's lives?